So today, as you fall asleep, I have researched every single unsolved math problem throughout history, and we are going to go through them slowly to help you relax. Let's begin. So, let's start from the very beginning with the problem that most mathematicians will tell you is the most important unsolved question in all of pure mathematics. Let's go back to the year 1859. There is a German mathematician named Bernhard Riemann, and he is 32 years old and probably a little nervous because he has just been elected to the Berlin Academy of Sciences, and they are expecting him to submit a paper. He submits one. It is 8 pages long. 8 pages. And those 8 pages contain an idea so deep and so strange that 165 years later, with all of our computers and all of our mathematics, we still cannot prove it. The paper was about prime numbers. And to understand what Riemann was doing, you have to understand a little bit about what makes prime numbers so strange. A prime number is a counting number bigger than 1 that can only be divided evenly by itself and by 1. So 2 is prime, 3 is prime, 5 is prime, 7, 11, 13, 17, 19, 23. They keep going, these numbers, scattered out across the number line, like stars scattered across the sky. They never completely stop. There are infinitely many of them. We have known that since the ancient Greeks. Euclid proved it more than 2,000 years ago with one of the most elegant little proofs in all of mathematics. You assume the list of primes is finite, multiply them all together and add 1, and the result cannot be divisible by any prime on your list, which means you missed at least one contradiction. The list cannot be finite, but here is the thing. Even though we know they never stop, we cannot really predict them. There is no pattern you can write down that tells you where the next prime number is going to show up. They seem almost random. You get gaps between primes that are very small, like the gap between 2 and 3, which is just 1 step, and then you get enormous gaps between the prime numbers 1,129 and 1,151. There is a gap of 22. Just silence. 22 numbers in a row that are not prime. And the further out you go into the number line, the bigger and more unpredictable these gaps tend to get. So mathematicians in the 19th century were asking, is there any structure to this apparent randomness? Is there any deep regularity hiding underneath the chaos of the primes? And Riemann had an idea. He said, instead of looking at primes directly, what if we look at a special function, a machine for turning numbers into other numbers that somehow encodes information about the primes inside it? The function he invented is called the Riemann zeta function, and at its most basic form, it is actually something you might have seen before. If you take 1 and then add 1/2, and then add 1/3, and then 1/4 and 1/5, and so on forever, you get an infinite series. The zeta function is a generalization of this. It takes an input and tells you the value of that kind of infinite sum, but with the input controlling the power to which you raise the denominators. And here is where it gets genuinely weird. Riemann used a technique called analytic continuation to extend this function so that it works not just for ordinary numbers, but for complex numbers. Complex numbers are numbers that have two components, a real part and an imaginary part. The imaginary part involves the square root of -1, which is a thing that cannot exist if you only allow ordinary numbers, but which mathematicians decided to just invent and found out that doing so unlocked enormous new territories of mathematics. So, once you extend the zeta function to the complex plane, something remarkable happens. The function has zeros, points where the output is exactly 0. Some of these zeros are obvious and boring. They happen at -2 and -4 and -6 and all the negative even integers. Riemann called these the trivial zeros. But there are other zeros, the non-trivial zeros, and these are the interesting ones, the ones that matter. When Riemann computed a few of these non-trivial zeros, he noticed something. They all seemed to land on a very specific vertical line in the complex plane, the line where the real part is exactly 1/2. Not 1/3, not 2/3, not 1/4, exactly 1/2. And Riemann said, almost as a side note, almost like he was thinking out loud rather than making a formal claim, that it is very likely that all of the non-trivial zeros lie on this line. That sentence, that casual observation in an 8-page paper became the Riemann hypothesis. The reason this matters so deeply, the reason mathematicians care about it so intensely, is because of what it would imply about prime numbers if it were true. The zeros of the zeta function are directly connected to how prime numbers are distributed. The location of these zeros controls the errors in our estimates of how many primes there are up to a given number. If all the zeros are on the 1/2 line, then those errors are as small as they possibly could be. The primes, while still irregular and seemingly random, would have a kind of deep orderliness underneath them, a hidden rhythm, and if even 1 zero were somewhere else, even 1 somewhere off that line, then the errors in our prime number estimates would blow up in ways that would mean our whole picture of the primes is significantly more chaotic than we thought. So here is where things stand today. Computers have checked the first 10 trillion non-trivial zeros of the Riemann zeta function, 10 trillion, and every single one of them sits exactly on the 1/2 line, not slightly off, exactly on it. You might think, okay, 10 trillion is a lot, that is basically a proof, right? But in mathematics, it does not work that way. There are many examples in math of things that appear to be true for millions or even billions of cases and then turn out to be false. The fact that 10 trillion zeros cooperate does not mean the 10 trillion and 1 will. We need a proof that covers every single zero, every one of the infinitely many non-trivial zeros, all at once, and nobody has that proof. The Clay Mathematics Institute, when they made their famous list of the 7 most important unsolved math problems in the year 2000, put the Riemann hypothesis on the list and offered $1 million to anyone who could solve it. Over 25 years later, the money is still sitting there. Some of the greatest mathematicians who ever lived have tried. David Hilbert, who made a famous list of 23 problems at the start of the 20th century and included the Riemann hypothesis as number 8, once said that if he were to wake up after sleeping for 500 years, the first question he would ask is whether the Riemann hypothesis had been proved, and that was over 100 years ago. He has been asleep a long time. There is one approach to the Riemann hypothesis that a lot of people find particularly beautiful. It involves the connection between the zeros of the zeta function and something called random matrix theory, which is a branch of mathematics concerned with the statistical properties of large matrices with random entries. In the 1970s, a mathematician named Hugh Montgomery was at a tea party at the Institute for Advanced Study in Princeton, and he got chatting with Freeman Dyson, who was one of the most famous physicists alive at the time. Montgomery told Dyson about some work he had been doing on how the zeros of the zeta function are spaced relative to each other, and Dyson stopped him and said, "Those numbers you are describing, I have seen those before. They come up when you study the energy levels of heavy atomic nuclei. The spacing between zeros of the Riemann zeta function appear to match the spacing between energy levels in quantum physics, two completely separate fields connecting through an identical mathematical structure. That connection has never been fully explained, but it suggests that somehow, deep underneath everything, the primes are connected to the physics of the universe in a way we do not understand yet. So, the Riemann hypothesis is not just a question about primes. It is a window into some deeper layer of mathematical reality that we have not found our way into yet. And the strange thing is how many other results in mathematics are conditional on the Riemann hypothesis being true. Over the years, mathematicians have proved enormous numbers of results that begin with the phrase, "Assuming the Riemann hypothesis is true, then this other thing is also true." There are hundreds of theorems that depend on it. It sits underneath so much of modern analytic number theory, like a foundation stone, except we cannot prove the foundation stone is actually there. We have built an enormous structure on top of it, and the structure seems stable, but we have never been able to confirm that the ground is solid. If the Riemann hypothesis turned out to be false, it would not just fail to solve a problem, it would collapse an entire wing of mathematics that has been under construction for over a century. results that had been thought of as theorems would revert to the status of open questions. The edifice would need to be rebuilt from scratch in that area. There is another direction worth thinking about. The Riemann zeta function is one of a whole family of related functions, all of which have their own versions of the same idea. There are related functions associated to elliptic curves, to algebraic varieties, to number fields. Each one has its own critical line, its own version of the question. For some of these related functions, the analogous statement has been proved. André Weil proved a version for functions associated to curves over finite fields in 1948. Pierre Deligne extended this to higher dimensional shapes in 1973 and won the Fields Medal partly for this work. So we know the pattern holds in those settings. But the original one, the one about the actual complex numbers, the one Riemann wrote about in 1859, remains unproved. There is a beautiful way of putting what the Riemann hypothesis is really saying if you translate it away from the technical language. It is saying that the prime numbers are distributed as randomly as they possibly could be, given their overall density. The zeros of the zeta function encode the fluctuations in the distribution of primes above and below the smooth trend. If all the zeros are on the 1/2 line, those fluctuations are minimally structured, essentially as close to pure randomness as a deterministic sequence can get. The primes look random. They hide their pattern as well as any sequence of numbers possibly could. That is what the Riemann hypothesis is claiming. It is a statement about the depth of the disguise the primes wear. Okay, so now let's look at something that is almost the opposite of the Riemann hypothesis in terms of how it sounds when you first hear it. The Riemann hypothesis sounds technical and complicated, and it is. What we're going to look at next sounds like a game you could play with a 10-year-old, but it is also completely unsolved. In 1937, a German mathematician named Lothar Collatz, who was 26 years old at the time, wrote down a simple game involving positive whole numbers. The game has 2 rules. If you have an even number, divide it by 2. If you have an odd number, multiply it by 3 and add 1. That is all. Then you take the result and do it again and again and again. You keep going. The question Collatz asked was, if you start with any positive whole number and keep following these rules, will you always eventually reach the number 1? Let's actually play it for a second. Start with the number 6. 6 is even, so you divide it by 2. You get 3. 3 is odd, so you multiply by 3 and add 1. You get 10. 10 is even, so divide by 2. You get 5. 5 is odd, so 3 times 5 plus 1 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. 6 steps to 1. Now try 27. 27 is odd, so 3 times 27 plus 1 is 82. 82 divided by 2 is 41. 41 is odd, so 3 times 41 plus 1 is 124. You keep going. 27 takes 111 steps to finally reach 1. Along the way, the sequence reaches a peak of 9,232 before finally coming back down. The sequence shoots up, comes down, shoots up again, eventually spirals down to 1. Always, at least, for every number anyone has ever tried. Computers have checked this for every number up to roughly 295 quadrillion. That is a 2 followed by 17 zeros. Every single one of them eventually reaches 1. Not one exception has ever been found, and yet nobody can prove it. This is the thing that makes the Collatz conjecture so weird. It is not that the problem is obscure. Paul Erdős, who was one of the most prolific mathematicians of the 20th century, and a man who genuinely spent his entire life doing mathematics, said about it that mathematics is not yet ready for such problems. He said this in a way that was meant to suggest that the problem is not merely hard, it is somehow outside the range of things current mathematics knows how to approach. Think about why that might be. The sequence for any given starting number is totally unpredictable. You cannot look at a number and know in advance how it will behave. The number 5 takes 5 steps. The number 27 takes 111 steps. The number 871 takes 178 steps. There is no formula, no shortcut. You just have to run the sequence and watch what happens. This unpredictability is the core of why it is so hard to prove. A proof would need to work for every possible starting number, including numbers so large that no computer could ever compute their sequence, and there is no obvious structure to grab onto. One of the most appealing ways of thinking about the Collatz conjecture is to think about what the rules are doing statistically. When you apply the 2 rules over and over, on average, is the sequence going up or going down? Well, if a number is even, dividing by 2 halves, it. If a number is odd, multiplying by 3 and adding 1, then dividing by 2 on the next step, since you just made an even number, gives you roughly 3 halves of the original. So on average, you might expect the sequence to shrink by a factor of 3/4 with each pair of steps. 3 halves times 1 half is 3/4, and 3/4 is less than 1, which means on average the sequence is going down. So in some statistical sense, you would expect the sequence to keep shrinking until it reaches 1. But this is not a proof. It is just an argument about averages. The sequence for a specific number does not have to follow the average. It might be a special case where the sequence keeps going up forever, or where it enters some other cycle that does not include 1. Nobody has ever found such a number, but nobody has proved one cannot exist. Terence-Tao, who is probably the most talented mathematician alive today and someone who has won every major prize in mathematics, published a major paper on the Collatz conjecture in 2019. He showed that almost all starting numbers do eventually reach a number very close to 1. Not all of them, not exactly 1, but close. It was a genuine step forward, the kind of thing that made mathematicians sit up and take notice. But it is still not a proof. What Tao's result actually says is quite beautiful in its own right. He proved that for any function that grows more slowly than logarithmically, almost all starting numbers will eventually reach a value below that function applied to the starting number. So if your function is the logarithm of the logarithm, almost all starting numbers will eventually go below that extremely small value. This says the sequences come down to almost 0, almost surely, but not quite 0, not quite 1. The gap between almost all and all is where the conjecture lives. And that gap, mathematically speaking, is enormous. Almost all could still leave infinitely many exceptional starting numbers. There could be infinitely many starting numbers that never reach 1, and they could still form a set so rare that they have 0 density in the whole numbers. Tao's result would not rule that out. There is a deep reason why the Collatz conjecture connects to some of the hardest problems in mathematics. The sequences it generates are essentially unpredictable. The sequence for any starting number bounces around in a way that looks, from a statistical standpoint, completely random, and yet it is completely deterministic. There is no randomness involved. Every starting number has exactly 1 sequence, but the sequence's behavior has no discernible structure that we can latch onto. This is related to something called pseudo-randomness in mathematics. Numbers that are generated by a deterministic rule but behave statistically like random numbers. Prime numbers are a famous example of this, which is part of why questions about primes and questions about Collatz sequences feel related, even though they come from very different places. Next, let's stay right here in the world of whole numbers and go back even further in time, all the way back to the year 1742, and a letter. In June of that year, a Prussian mathematician named Christian Goldbach wrote a letter to the Swiss mathematician Leonhard Euler. Euler is one of the most famous mathematicians who ever lived, the man who produced more mathematics than almost anyone in history, the man who worked so hard that he lost the sight in one of his eyes and kept going. Goldbach wrote to Euler because he had noticed something about even numbers that he thought was interesting. He had noticed that every even number bigger than 2 seems to be the sum of 2 prime numbers. Take 4. 4 equals 2 plus 2. 2 is prime, so that works. Take 6. 6 equals 3 plus 3. 3 is prime. Take 8. 8 equals 3 plus 5. Both prime. Take 10. 10 equals 3 plus 7 or 5 plus 5. Both of those work. 28 equals 5 plus 23. 100 equals 3 plus 97 or 11 plus 89 or 17 plus 83. No matter what even number you pick, it always seems to fall apart into two primes. Goldbach noticed this and wrote it down for Euler, wondering if Euler could prove it. Euler could not prove it, and neither could anyone who came after him. In more than 280 years, nobody has proved it, even though the pattern holds for every even number that has ever been checked. Computers have verified Goldbach's conjecture for every even number up to 4 quintillion, 4 followed by 18 zeros. Every single one splits into two primes. Not one exception anywhere. The sheer scale of the checking makes it feel ridiculous that we cannot prove it. We have tested this across a range of numbers so vast that it would take longer than the age of the universe to say them all out loud, one by one. And yet mathematics does not care about scale. Mathematics cares about proof. And we do not have a proof. The closest result to a proof is something called Chen's theorem, proved by the Chinese mathematician Jingrun Chen in 1973. Chen proved that every large enough even number can be written as either the sum of two primes or the sum of a prime and a number that is itself the product of exactly two primes. A number that is the product of exactly two primes is sometimes called a semi-prime. 15, for example, is a semi-prime because 15 equals 3 times 5. Chen got us one step away from Goldbach's conjecture, one stubborn step. There is something deeply satisfying about Goldbach's conjecture as a piece of mathematics. The statement is something you can explain to a child. Try it with any even number. Keep trying. You will always find two primes that add up to it. The pattern is right there, totally visible, totally verifiable in specific cases. And yet the proof is so far out of reach that the world's best mathematicians for nearly 3 centuries have not found it. This asymmetry between the visibility of the pattern and the invisibility of the proof is one of the things that makes number theory so addictive and so maddening. The numbers are right there. The pattern is right there, and you still cannot touch it. Part of why the conjecture is so hard is that it is mixing together two very different things: addition and primality. Primes are defined in terms of multiplication. A prime is a number that cannot be written as a product of smaller whole numbers. But Goldbach's conjecture is asking about addition. It is saying that every even number is the sum of two numbers that are defined by a multiplicative property. The additive structure and the multiplicative structure of the whole numbers are deeply entangled, and understanding how they interact is one of the core challenges in number theory. This tension between addition and multiplication is not unique to Goldbach. It shows up everywhere in number theory. The Riemann hypothesis is, in a sense, also about distension. The zeta function encodes multiplicative information about primes through its product formula, but it is also a sum. The sum and the product formula are equal, and that equality carries enormous information about the primes. Goldbach is a different manifestation of the same underlying mystery. There is a probabilistic argument that the conjecture should be true, and it is worth sitting with. The prime number theorem tells us that the chance that a number near n is prime is roughly 1 over the logarithm of n. So, the chance that two numbers near n are both prime is roughly 1 over the logarithm of n squared. There are roughly n ways to split an even number of size around 2n into two parts. So, the expected number of ways to write a large even number as a sum of two primes is roughly proportional to n divided by the logarithm of n squared, which grows without bound. So, not only should every large even number be expressible as a sum of two primes, it should be expressible in an enormous number of ways. And indeed, computers confirm that the number of Goldbach representations grows and grows fast. But this probabilistic argument is just that, probabilistic. It is a heuristic. It suggests truth, but does not constitute proof. In mathematics, you need the real thing. And now, let's look at something closely related, a question about pairs of prime numbers. A twin prime is a pair of prime numbers that differ by exactly 2. So, 3 and 5 are twin primes. 5 and 7 are twin primes. 11 and 13, 17 and 19, 29 and 31, 107 and 109. Twin primes pop up all over the place, especially when you are working with smaller numbers. But as you go further and further out along the number line, prime numbers get rarer and more spread out. The gaps between them get bigger on average. So, do twin primes also get rarer and eventually stop? Or do they keep going forever, all the way out to infinity? The twin prime conjecture says they go on forever. There are infinitely many twin prime pairs. No matter how far out you go, you will always eventually find two primes sitting exactly 2 apart. Mathematicians have believed this for a very long time and have never found a counter-example. The largest known pair of twin primes as of recent years consists of 2 numbers, each with over 800,000 digits. They are gigantic, far beyond anything a human being could write out. And yet there they are, sitting 2 apart, both prime. But again, we cannot prove there are infinitely many. And then, in 2013, something happened that genuinely shook the mathematical world. A relatively unknown mathematician named Yiteng Zhang, who was working as a lecturer at the University of New Hampshire and had spent years struggling to get his career going, submitted a paper to the Annals of Mathematics. one of the most prestigious journals in mathematics. The paper proved something nobody had ever proved before. Zhang showed that there are infinitely many pairs of prime numbers that differ by at most 70 million, not 70 million. But still, this was the first time anyone had ever proved that prime numbers have a bounded gap infinitely often. Before Zhang's paper, we had no proof that prime numbers could not just spread out infinitely, with gaps growing without bound. Zhang's paper proved that there is some finite number, some gap, that is realized infinitely many times. The mathematical community was electrified. And then something remarkable happened. Within months, a collaborative project called Polymath got to work reducing Zhang's bound. Zhang had said the bound was 70 million. Within weeks, the Polymath project had reduced it to millions, then hundreds of thousands, then thousands. Within a year, James Maynard, a young British mathematician, had independently brought the bound down to 600. The Polymath project eventually got it down to 246. So we now know that there are infinitely many pairs of prime numbers that differ by at most 246. We need to get that down to 2, just 2. And that step from 246 to 2 is the twin prime conjecture, and it remains out of reach. The story of Zhang and Maynard is one of the most inspiring recent chapters in mathematics. Zhang was in his late 50s when he proved his result after years of working in relative obscurity. He had worked at a Subway restaurant at one point. He had struggled to find academic positions. And then he sat down and proved something that had been out of reach for everyone who came before him, and cracked open a door that had been shut for centuries. What is remarkable about Zhang's proof is not just the result, but the method. The tools he used had been sitting around in the literature for years. Mathematicians knew about the sieve methods he was applying. They knew about the structure of the arguments involved. But Zhang found a way to combine them that nobody had seen before. A specific technical insight about how to handle a certain kind of average that allowed everything to click into place. Maynard's work was different. Maynard found an entirely independent approach, simpler in some ways than Zhang's, that immediately gave a much better bound. His method generalized in a way that Zhang's did not, which is why the Polymath project was able to reduce the bound so dramatically using Maynard's techniques rather than Zhang's. The number 246, the current best bound, represents the state of the art as of recent years. Getting from 246 down to 2 requires proving what is called the Elliott-Halberstam conjecture, a statement about the distribution of primes in arithmetic progressions at a level beyond what we can currently prove. Assuming the Elliott-Halberstam conjecture, Maynard's methods can get the bound down to 6, still not 2, but closer, and assuming a stronger version of that conjecture, the methods might reach too. But these are conditional results. They assume things we cannot prove. So the twin prime conjecture remains tantalizing. We are closer than we have ever been. The tools now exist to get bounded gaps. But the final step from a small bound to the exact bound of 2 requires either something new or the resolution of a problem that is itself deep and hard. Okay, and now let's drift away from pure number theory and into a world that feels completely different. A world where the question is not about numbers at all, but about something much more practical and in some ways much more consequential. Let's imagine you are trying to plan the most efficient road trip. You have 50 cities you want to visit. You want to visit each one exactly once and end up back where you started. And you want the total distance you travel to be as short as possible. This is called the traveling salesman problem, and it is one of the most famous problems in computer science. Here is the thing. If someone hands you a specific route and says, "Is this the shortest possible route?" you can check that relatively quickly. You can add up all the distances and compare it to other routes. Checking a solution is easy, but finding the best solution in the first place, that is where things get brutal. With 50 cities, the number of possible routes you would have to check is 50 factorial. 50 times, 49 times, 48 times, 47, all the way down to 1. That number is so big it would take longer than the age of the universe to check every route, even on the fastest computers alive today. So in practice, we use clever approximations. But nobody knows of a genuinely fast way to find the true optimal answer. The problem that encapsulates this is called P versus NP. And here, P and NP are not acronyms you need to look up. They are shorthand for 2 specific ideas. P stands for polynomial time, which is the category of problems a computer can solve quickly. Quickly means that the time it takes does not explode catastrophically as the size of the problem grows. Adding numbers is in this category. Sorting a list is in this category. Multiplying numbers is in this category. The other category, NP, stands for non-deterministic polynomial time. Problems in this category are ones where a solution, if someone hands it to you already formed, can be checked quickly. The traveling salesman problem is in this second category. If someone hands you a route and says, "This is the optimal one," you can check whether it works in reasonable time. The question is, are these 2 categories the same? Is every problem whose solution can be checked quickly also a problem that can be solved quickly? That is the whole question. That is what P versus NP is asking. Almost every computer scientist and mathematician alive believes the answer is no. They believe there are problems that are easy to verify, but genuinely, fundamentally hard to solve. But nobody has proved this. And here is what makes this more than just an abstract puzzle. If the answer turned out to be yes, that they are the same, it would mean that any problem whose solution can be checked quickly can also be solved quickly, and the consequences would be staggering. Essentially, all of modern internet security is built on the assumption that these two categories are different. When you send a credit card number over the internet, it is encrypted using a system that is easy to lock but should be extremely hard to crack. If this problem were resolved the wrong way, those systems would potentially be breakable. The entire infrastructure of secure communication would be vulnerable. At the same time, it would mean that problems in medicine and optimization and protein folding that currently require enormous supercomputers could potentially be solved efficiently. You could design perfect drug molecules. You could optimize the global supply chain. The world would look completely different. The difficulty of proving that these two categories are genuinely different comes from the fact that you are trying to show that no algorithm, not just the ones we have tried, but any algorithm whatsoever, could efficiently solve these problems. Proving a negative about the space of all possible algorithms is extraordinarily hard. The space of all possible algorithms is so large and so strange that mathematicians do not currently have the tools to reason about all of it at once. There are results called complexity barriers that essentially tell us that many of the most natural-seeming approaches to this proof cannot work. Mathematicians have hit walls from multiple directions. One of the deepest barriers is called the relativization barrier, discovered by Theodore Baker, John Gill, and Robert Solovay in 1975. They showed that the question cannot be resolved by the most powerful technique mathematicians had been using at the time, a technique called oracle arguments or relativization. This was devastating because most of the proofs in computability theory at that point used this technique in one move. It ruled out the entire most natural toolkit. Then, in the 1990s, another barrier was discovered, called the natural proofs barrier, by Alexander Rasbarov and Stephen Rudich. They showed that any proof strategy that works a certain natural way, that builds on showing lower bounds on the computational complexity of specific functions, cannot work either. And again, this ruled out a huge class of attempted approaches. And then the algebrization barrier was discovered by Scott Aronson and Avi Wigderson, ruling out yet another class of approaches. Each of these barriers says, whatever the proof is, if it exists, it has to be doing something completely different from what we have tried. The proof cannot use the most natural tools. It cannot work in the most natural ways. It has to be novel in a way we cannot currently articulate. That is a deeply uncomfortable place to be after decades of sustained effort. There is also a philosophical wrinkle here that mathematicians find uncomfortable to sit with. One of the problems that sits in the category of hard to solve but easy to verify is the problem of finding proofs themselves. Given a mathematical statement and a proof of it, checking the proof is quick, but finding the proof in the first place is hard. If these two categories turned out to be the same, it would mean that finding mathematical proofs is, in principle, as easy as checking them. It would mean that mathematics could be automated, that given a mathematical statement, a sufficiently powerful computer could always find a proof quickly if one exists. Most mathematicians find this conclusion so strange and so contrary to their experience of doing mathematics that it reinforces their belief that the two categories really are different. So next, let's move from logic and computation into something that touches the physical world, something about the way fluids move. In 1822, Claude-Louis Navier, a French engineer, and later in 1845, George Gabriel Stokes, an Irish mathematician and physicist, wrote down a set of equations that describe how fluids move. These equations account for velocity, pressure, density, and the viscosity of the fluid. They have been used for almost 2 centuries to design aircraft, to model weather, to simulate ocean currents, to understand blood flow in the human body. They work extraordinarily well in practice. Engineers trust them completely. But here is the problem. Nobody has been able to prove that these equations are always well behaved in 3 dimensions. Well behaved means that they do not produce infinities, that they do not blow up. If you start with a smooth, gentle flow and then ask the equations to evolve it forward in time, do the solutions stay smooth and finite forever? Or can they develop singularities, points where the velocity or pressure shoots off to infinity in 2 dimensions? This question has been answered. 2-dimensional fluids, mathematically speaking, always behave well. In 3 dimensions, we do not know. Nobody has proved that 3-dimensional solutions always stay smooth, and nobody has proved that they can blow up either. We do not know which way it goes. This might seem like a purely academic question. Actual water, actual air, does not develop infinite velocity, but the concern is that the equations, if they can blow up in finite time, might not actually be capturing the full story of fluid motion. Turbulence, which is something we all experience when a plane hits rough air, remains deeply, poorly understood mathematically. The question of whether these equations always produce smooth solutions is one of the deep underlying questions about whether our mathematical description of fluid motion is complete and consistent. The Clay Mathematics Institute made this one of the 7 most important unsolved problems. $1 million sits waiting for either a proof that 3-dimensional solutions always remain smooth, or a proof that they can blow up. Terence-Tao has done serious work on a variant of this problem, showing that certain modified versions of the Navier-Stokes equations can blow up in finite time. This does not mean the real equations blow up, but it does suggest that the tools needed to prove they do not blow up will have to be very, very sharp. The proof, if it comes, will need to exploit something specific about the structure of the true equations that the modified versions do not share. One way to understand why this is hard is to think about turbulence. When water moves slowly around a smooth obstacle, the flow is laminar, meaning the water moves in smooth, predictable layers. But when the water moves faster or the obstacle is more complex, the flow becomes turbulent. It breaks into swirls and eddies and chaotic patterns that are extraordinarily difficult to predict, even with the best computers. Turbulence is one of the few major unsolved problems in classical physics, in the sense that we do not have a complete mathematical theory of when and how it arises. The Navier-Stokes equations describe turbulent flow perfectly well, in the sense that they are the correct equations. The issue is that we cannot solve them in closed form for turbulent situations. We can simulate them numerically with a computer discretizing the space and time and approximating the solution, and those simulations work well. But solving them analytically, understanding them theoretically, is far beyond current ability. The existence and smoothness question is asking something slightly different from turbulence, but they are related. Turbulence involves very rapid, very complex variations in velocity over small distances. If the velocity can blow up to infinity at some point in finite time, that would be an extreme version of this rapid variation. A proof that solutions always stay smooth would, in a sense, set an upper limit on how badly behaved the solutions can get. It would say that no matter how chaotic the flow becomes, no matter how turbulent, the velocity always stays finite, always stays a proper function rather than blowing up to infinity. So, this problem, though it sounds abstract, is connected to something very concrete: the limits of how well we can mathematically describe the physical world around us. Now, let's look at something that connects mathematics and physics in a different way. In 1954, two physicists named Chen-Ning Yang and Robert Mills wrote down a set of equations that generalize Maxwell's equations for electromagnetism. Maxwell's equations describe how electric and magnetic fields behave. Yang and Mills extended this framework to describe other forces of nature. The equations they wrote down became the backbone of the standard model of particle physics, the theory that describes essentially everything we know about how fundamental particles work. The standard model is extraordinarily successful. It has made predictions confirmed by experiments to astonishing precision. It describes quarks and electrons and neutrinos and the particles that carry forces. But here is the mathematical problem. The equations describe fields in quantum mechanics, and quantum mechanics is genuinely hard to put on rigorous mathematical footing. Physicists work with these equations all the time and get correct answers, but the mathematical framework they are using involves things like path integrals, which are extraordinarily powerful calculation tools that do not yet have a fully rigorous mathematical meaning. The problem has two parts. The first is to actually prove that a quantum version of this theory exists as a rigorous mathematical object, not just to use it as a calculation tool, but to prove that the mathematical objects it describes are well defined. The second part is called the mass gap. In physics, the mass gap refers to the difference in energy between the lowest possible energy state of a quantum field and the next lowest energy state. For the quantum theory described by these equations, all of the particles it describes should have a positive mass, no massless particles, and this is consistent with what we observe experimentally. But proving it mathematically, the kind of proof that would make a mathematician satisfied, has never been done. The physical evidence is overwhelming. Experiments confirm that the relevant particles are massive. Simulations on powerful computers are consistent with there being a mass gap, but a mathematical proof has not been written down. Solving it would require essentially building from scratch a rigorous mathematical version of quantum field theory, the framework that underlies all of modern particle physics. That is a monumental task that would likely require new mathematics that has not been invented yet. Next, let's travel into a different landscape entirely, away from physics and numbers and into pure geometry, but a very strange kind of geometry. In algebraic geometry, mathematicians study shapes called algebraic varieties. An algebraic variety is the set of all solutions to a system of polynomial equations. Polynomial equations are equations involving powers of variables like x squared plus y squared equals 1, which gives you a circle, or more complicated things in more dimensions. The solutions to these systems of equations form shapes, sometimes smooth and curved, sometimes having corners and irregularities. These shapes can be studied using something called cohomology. Cohomology is a way of assigning algebraic structures to topological spaces in a way that captures information about the shape's structure. It is one of the central tools of modern pure mathematics. William Valence Douglas Hodge, a Scottish mathematician working in the mid-20th century, made a conjecture about the connection between two different kinds of structure on these algebraic varieties. He asked, take a certain kind of algebraic variety, specifically a smooth, complex, projective variety, which is a type of shape described by polynomial equations with complex number coordinates. Look at its cohomology classes. Some of these cohomology classes have a special property. They can be represented by algebraic cycles, roughly speaking, by subshapes that are themselves described by polynomial equations. Hodge conjectured that certain cohomology classes that look from the analytic side of things like they might be algebraic actually are algebraic. Here is a way to feel the flavor of this problem. You have a shape. You can measure certain properties of that shape using analysis, using techniques that involve smoothness and calculus. And you can also describe properties of that shape using algebra, using polynomial equations. The Hodge conjecture says that these two descriptions agree in a specific way. The analytical picture and the algebraic picture line up. What makes it hard is that the analytic tools and the algebraic tools are very different in nature. Bridging them requires understanding deep connections between two different mathematical languages, and those connections have proven resistant to the tools currently available. The Hodge conjecture was added to the Millennium Prize list. Partial results have been proved. For varieties of low dimension, the conjecture has been verified, but the general case remains open. Now let's look at a problem that sits right at the intersection of number theory and geometry, two areas of mathematics that have surprised everyone by being deeply intertwined. This one starts with a family of curves called elliptic curves. Despite the name, elliptic curves have nothing to do with ellipses. They are curves described by equations of the form y squared equals x cubed plus some constant times x plus another constant, where the constants are chosen to ensure the curve does not have any sharp corners or self-intersections. Elliptic curves are beautiful mathematical objects. They show up in an enormous variety of contexts. Andrew Wiles used them to prove Fermat's last theorem in 1995, the famous problem that had been unsolved since 1637, and which stated that for any whole number bigger than 2, there are no positive whole number solutions to the equation you get by adding 2 identical powers and claiming they equal a third identical power. So you cannot have 2 cubes that add to a third cube. You cannot have 2 fourth powers that add to a fourth power, and so on. Wiles proved it, but his proof was over 200 pages and went through elliptic curves. Elliptic curves are also used in modern cryptography. The security of many encryption systems, including ones that protect communications on your phone, is built on the difficulty of certain computations involving elliptic curves. Now, the question at the heart of the Birch and Swinnerton-Dyer conjecture is about the rational points on an elliptic curve. A rational point is a point where both coordinates, the x and the y, are rational numbers, meaning fractions. You might have no rational points on a given elliptic curve, or a finite number, or infinitely many. Brian Birch and Peter Swinnerton-Dyer were mathematicians working at Cambridge in the 1960s. They used one of the early computers available to universities at the time to study a large number of elliptic curves and their rational points. They found a striking pattern. The number of rational points on an elliptic curve seemed to be related to a certain function derived from the zeta function but adapted to the specific curve, evaluated at a specific value. Specifically, they conjectured that an elliptic curve has infinitely many rational points if and only if this adapted function is equal to 0 at a certain spot. This conjecture, if proved, would give a precise way of predicting whether an elliptic curve has infinitely many rational solutions or just finitely many. It would connect the discrete world of rational points with the analytic world of functions in a deep and calculable way. Very partial results have been proved. The conjecture has been verified in many specific cases, but the general proof remains out of reach. What makes this conjecture so important is partly the connection it makes between two very different types of mathematical objects, and partly what it says about our ability to find solutions to equations in whole numbers. Mathematicians have been studying solutions to polynomial equations in whole numbers since ancient times. The ancient Babylonians knew about Pythagorean triples, integer solutions to x squared plus y squared equals z squared, like 3, 4, 5. The question of which polynomial equations have integer or rational solutions, and how many, is one of the oldest questions in mathematics. The Birch and Swinnerton-Dyer conjecture, if proved, would give a completely general and computable answer to this question for one of the most important families of equations. It would turn what is currently a mystery into a calculation. And now, let's look at a problem that is more recent compared to the others, but which has already generated one of the most unusual situations in the history of mathematics. In 1985, two mathematicians named David Masser and Joseph Oesterle formulated a conjecture about three whole numbers they called A, B, and C, where A plus B equals C, and the three numbers share no common factors. The conjecture is about the relationship between these three numbers and their prime factorizations. When you take a whole number and completely factor it into primes, you get a collection of prime numbers with their multiplicities. For example, 1080 can be written as 2 cubed times 3 cubed times 5. The prime factors are 2, 3, and 5. Now define something called the radical of a number. The radical is the product of its distinct prime factors, but with each prime appearing only once, regardless of how many times it divides the number. So the radical of 1080 would be 2 times 3 times 5, which is 30. All the repeated prime factors have been stripped away. The conjecture says that for any such triple where A plus B equals C and they share no common factor, the number C is always less than the radical of A times B times C raised to a power slightly above 1. In other words, when you strip away the multiplicities of the prime factors, the resulting product always dominates C. There can only be finitely many exceptions for any fixed exponent above 1. This might sound like a dry, technical statement, but the consequences of proving it would be enormous. The conjecture implies, almost as a special case, a proof of Fermat's last theorem that is much shorter and more direct than Wiles's 200-page proof. It implies results about the distribution of perfect powers. It connects a huge number of different results in number theory in a single unified statement. In 2012, a Japanese mathematician named Shinichi Mochizuki posted a series of 4 papers online that he claimed proved this conjecture. The papers were written in a completely new mathematical language that Mochizuki had invented over several decades. The papers together were over 500 pages long and described the framework so novel and so different from anything else in mathematics that most mathematicians found them essentially unreadable. For years, mathematicians struggled to understand what Mochizuki had done. In 2018, two German mathematicians named Peter Scholze and Jacob-Stix visited Mochizuki in Japan and went through the papers carefully. They came back and said they had found what appeared to be a serious error in one of the key steps. Mochizuki disagreed and has continued to stand by his proof. The mathematical community is still divided on this. Some mathematicians in Japan have accepted the proof. Most mathematicians outside Japan remain skeptical. The papers have been officially published in a journal that Mochizuki himself edits, which added to the controversy. As of today, the status of this conjecture is genuinely unclear. It might be proved, and the community just cannot tell yet. It might have a subtle flaw. The mathematics is so strange and novel that the usual mechanisms of peer review have struggled to reach a verdict. This whole situation is fascinating in its own right because it reveals something about how mathematics actually works as a human activity. A proof that nobody can understand is not, in the practical sense, a proof that advances human knowledge. The community has to understand it. And Mochizuki's work has pushed right up against the limits of mathematical communication in a way that has no clear precedent. Okay, now let's shift completely into geometry, something that could not be more different in flavor. You are moving into a new apartment. You have a sofa. The sofa needs to go around a corner in a hallway. The hallway is 1 unit wide and it makes a right angle turn. What is the largest possible sofa, measured in terms of its two-dimensional cross-sectional area that can be moved around that corner? This is the moving sofa problem. It was first posed formally by the Canadian-Austrian mathematician Leo Moser in 1966. At first glance, this looks like a practical question with an obvious answer. You try a few shapes, you see which one fits. But actually making that rigorous, proving that you have found the absolute maximum possible area and not just a local maximum, is where the difficulty lies. A simple semicircle of radius 1, sitting lengthwise in the hallway, has an area of pi over 2, which is roughly 1.57, better than a square sofa, but probably not optimal. In 1968, Joseph Gerver proposed a specific sofa shape that is now called the Gerver sofa. It looks a bit like a telephone handset, with a curved outer edge and a concave notch cut into the inner edge. Its area is approximately 2.22. It is the largest sofa anyone has ever found that can navigate the corner. But is it the best possible? Is there some weirder, more complex shape that could have a slightly larger area and still get around the corner? Nobody knows. No proof exists that this is truly optimal. To prove optimality, you would need to somehow search over all possible shapes, which is an infinite dimensional space of possibilities, and show that none of them do better. The space of candidate shapes is rich and strange, and the constraints imposed by the corner are complex. In 2017, two mathematicians showed that any sofa must have area at most 2.37, so the answer lies somewhere between 2.22 and 2.37. Somewhere in that gap, there is also an extension where the hallway makes two turns, one left and one right, so the sofa has to navigate a shaped corridor. The sofa has to work in both directions, which imposes stronger symmetry constraints. The best known shape in this case has a smaller area than the Gerver sofa, which makes intuitive sense since the requirements are stricter. But proving optimality for this version is, if anything, harder than for the single-turn version. The moving sofa problem has this quality that many problems on this shelf share. It is embarrassingly easy to state, and the answer is probably close to what our intuition suggests. And yet, the machinery needed to formally confirm that intuition is deep and difficult. We know roughly where the answer is, we just cannot reach it. And now, let's look at a problem about coloring. Draw a flat, infinite plane. Now ask, what is the minimum number of colors you need to paint every point of this plane, such that no 2 points that are exactly 1 unit apart get the same color? This sounds bizarre. You are coloring every single point in the entire infinite plane, not just a finite collection of dots, but the question is completely precise and well defined. This problem was posed in 1950 by Edward Nelson, who was a first-year graduate student at the time. The answer, which is called the chromatic number of the plane, is at least 5 and at most 7. Why at most 7? Because there is a specific way of tiling the plane with hexagons of the right size, such that you can assign one of 7 colors to each hexagon and guarantee that no 2 same-colored hexagons are at unit distance from each other. So 7 colors are enough. Why at least 5? For almost 70 years, we only knew the answer was at least 4. People had found specific finite collections of points in the plane where you need at least 4 colors to ensure no 2 points at distance exactly 1 are the same color. And then, in 2018, something remarkable happened. A computer scientist and amateur mathematician named Aubrey de Grey, who is primarily known for his work on biological aging, sat down with some graph theory and a computer and found a collection of over 1,280 points in the plane where 4 colors are not enough. 5 are required. This instantly moved the lower bound from 4 to 5. The chromatic number of the plane is somewhere between 5 and 7, and that is where we still are. We do not know whether the true answer is 5, 6, or 7. De Gray's discovery was a genuine breakthrough after nearly 70 years of no progress, and it came from outside the usual circles of professional geometry, which was itself a remarkable thing. Next, let's look at something even older, a question about gaps between perfect squares. Take any whole number, call it n. Between n squared and the quantity n plus 1 squared, are there always prime numbers? That is the entire question. For every counting number n, does the interval between n squared and the next perfect square always contain at least one prime? Take n equals 1. Between 1 and 4, you have 2 and 3, both prime. Take n equals 2. Between 4 and 9, you have 5 and 7. Take n equals 3. Between 9 and 16, you have 11 and 13. Take n equals 10. Between 100 and 121, you have 103, 107, 109, and 113. Take n equals 100. Between 10,000 and 10,201, there are plenty of primes. Nobody has found an n where the interval is empty, and the intervals grow as n grows. The gap between n squared and the next perfect square is about 2n plus 1, which gets wider and wider as you go out. So they should be getting more comfortable for primes, not less. But proving this rigorously is another matter entirely. The prime number theorem, which tells us roughly how many primes there are up to a given number, gives averages. It cannot rule out the possibility that there are occasional long gaps, occasional unlucky intervals where no prime shows up. To prove this, you would need a result about the distribution of primes that is sharper and more precise than anything currently available. Adrien Marie Legendre proposed this around 1800. It has been open for more than 200 years. Now let's look at something that started with an amateur mathematician and ended up with $1 million prize still uncollected. Andrew Beal is a Texas banker and amateur mathematician. In 1993, he was working on variations of Fermat's last theorem and came across something. He noticed that whenever he had an equation where one whole number raised to a whole number power plus another whole number raised to a whole number power equaled a third whole number raised to a whole number power, and all three exponents were at least 3, the bases always seemed to share a common prime factor. For example, 2 to the third plus 2 to the third equals 2 to the fourth. Here the base is 2 in all 3 cases, so they obviously share a factor. Or consider 7 to the 6th plus 7 to the 7th equals 14 to the 6th. Here, 7, 7, and 14 all share the factor 7. Beal conjectured that every solution to this type of equation must have the three bases sharing a common prime factor. In other words, whenever three perfect powers add up this way, the bases cannot be completely unrelated to each other. He offered a cash prize for a proof or a counterexample. The prize has grown over the years and currently stands at $1 million. Nobody has proved it. Nobody has found a counterexample. Computers have searched through enormous ranges of values and found nothing that contradicts the conjecture. And now, let's look at a problem in three-dimensional geometry that has frustrated people for a remarkably long time. A rectangular box has three pairs of rectangular faces and four main diagonals, lines running through the interior from one corner to the opposite corner. A perfect cuboid would be a box where all 7 of the following distances are whole numbers: the 3 edge lengths, the 3 face diagonals, and the 1 space diagonal. Leonhard Euler found examples of boxes where the 3 edge lengths and the 3 face diagonals are all whole numbers, but the space diagonal is not. Euler's solution had edges of 240, 117, and 44. The 3 face diagonals are all whole numbers, but the space diagonal is not. So Euler found something called an Euler brick, which gets you 6 of the 7 conditions. Getting all 7, a perfect cuboid, has never been done. Nobody has ever found a perfect cuboid, and nobody has proved that one cannot exist. Any perfect cuboid would have to have at least one edge longer than 3 times 10 to the 12th power. So the smallest one, if it exists, is very large. But very large is not the same as non-existent. This problem sits in elementary number theory, requiring no advanced machinery even to state or understand, and yet it resists every attempt at either a construction or a proof of impossibility. Okay, next, let's look at a question about curves and squares that has been open for well over a century. Draw any closed curve in the plane, any shape at all. It could be smooth, it could be jagged, it could be extremely complicated. The only requirement is that it does not intersect itself. It is a simple closed curve. Now the question is, does the curve always contain 4 points that form a perfect square? This was posed by Otto Toeplitz in 1911. For smooth curves, curves without any sharp corners, the answer is yes. This was proved at different levels of generality by various mathematicians over the years. For curves that are allowed to have corners, the question is much harder. For some classes of curves with corners, the result has been verified. But for arbitrary, simple, closed curves, even very complicated ones with all sorts of corners and irregularities, the question is still open. In 2020, 2 mathematicians proved a beautiful related result, showing that every smooth, simple, closed curve contains not just one inscribed square, but actually a continuum of inscribed rectangles. This was a genuine breakthrough, but the full inscribed square problem for arbitrary curves is still unsettled. Now let's talk about something in algebra. A polynomial map is a function from some space to itself, where the output coordinates are given by polynomial functions of the input coordinates. The Jacobian of such a map is a matrix of derivatives. You can take its determinant, a single number that at each point tells you how the map is locally stretching or squishing the space. The question is, if the Jacobian determinant is everywhere a non-zero constant, does the map have a polynomial inverse? In other words, if the map is globally everywhere, locally invertible in this strong sense, is it globally one-to-one with a polynomial inverse? The Jacobian conjecture has been listed as a theorem and then shown to have an error in the proof multiple times. False proofs have been proposed, accepted briefly, then found to be flawed. It has attracted a remarkable number of incorrect proofs over the years, which itself is an interesting sociological fact about mathematics. The problem feels like it should be true, and feels like it should be provable, and yet every attempt finds a subtle error somewhere. And now, let's look at something in functional analysis. In a vector space, a linear operator is a map from the space to itself that respects its structure. An invariant subspace for such an operator is a subspace that the operator maps into itself. Every vector in the subspace gets sent to another vector still in the subspace. Every operator has two trivial invariant subspaces, the whole space itself and the zero subspace. The invariant subspace problem asks, does every bounded linear operator on an infinite dimensional Hilbert space, which is a type of infinite dimensional space with a notion of distance and angle, have a non-trivial closed invariant subspace? For finite dimensional spaces, the answer is yes. For operators on certain types of infinite dimensional spaces, the answer is no. Counterexamples exist. But for a general bounded linear operator on a general infinite dimensional Hilbert space, nobody knows. This problem has been described by some analysts as one of the most important open questions in operator theory. Now let's look at something about numbers that feels like a guiding star for the whole field of transcendence theory. Most numbers that arise naturally are algebraic, meaning they satisfy some polynomial equation with rational coefficients. The square root of 2 satisfies x squared minus 2 equals 0. But some numbers are transcendental. They are not solutions to any such equation. Pi is transcendental. So is e, the base of natural logarithms. A conjecture proposed by Stephen Schanuel in the 1960s makes a sweeping claim about transcendence. It says, if you take any collection of complex numbers that are linearly independent over the rational numbers, meaning no rational number combination of them is 0, then among all those numbers and their exponentials, at least as many of them as you started with are algebraically independent over the rational numbers. Algebraically independent means no polynomial equation with rational coefficients is satisfied by any combination of them. This single conjecture would imply, as special cases, essentially all known results about the transcendence of numbers like pi and e, and many more results that are currently conjectured but not proved. It would imply that pi and e are algebraically independent, meaning there is no polynomial equation with rational coefficients that is satisfied by pi and e together. Whether pi and e are algebraically independent is currently an open question on its own. It would imply that e raised to the power of pi is transcendental. It would essentially unlock the whole field of transcendence theory in one move. But Schanuel's conjecture itself is nowhere near proved. It is more of a guiding star than a theorem in progress. Now, let's look at something beautiful that sits in combinatorics and has an almost fairy tale quality to it. Imagine a circular running track. On this track, there are some runners. Each runner runs at a different constant speed. They all start at the same point at the same time. The question is, will each runner at some point in time be lonely? Lonely means that the nearest other runner is at least 1 over n times the circumference of the track away from them, where n is the total number of runners. The lonely runner conjecture says yes. Every runner will eventually be lonely. For 2 runners, this is easy. The 2 runners start together and one goes faster. Eventually, the faster runner laps the slower one, and they are halfway around the track from each other, both lonely. For 3 runners, it can be shown as well. For 7 runners, the conjecture has been proved. Any configuration of 7 runners on a circular track running at distinct speeds will have each runner experience a time when they are at least 1/7 of the track away from everyone else. For 8 or more runners, the conjecture is open. There is something poetic about this problem. It is about isolation, about the inevitability that even in a group of runners all chasing each other around a loop, each one will at some point be left alone, separated from the pack by at least a certain minimum distance. The proof for 7 runners required very clever arguments and was the result of years of work. The step from 7 to 8 seems to require genuinely new ideas. What makes the lonely runner conjecture interesting beyond its charm is that it connects to several other areas of mathematics. It is related to questions in Diophantine approximation, which is the study of how well real numbers can be approximated by rational numbers. It is related to questions about the distribution of sequences modulo 1, which is about the fractional parts of multiples of real numbers, and it connects to problems in combinatorics about covers of integers. The conjecture can be restated in several equivalent forms, and this multiplicity of equivalent formulations is itself a sign of depth. When a problem can be looked at from several completely different angles, and each angle leads to the same question, it usually means there is something substantial sitting at the center. The lonely runner conjecture has been verified by computer for small numbers of runners beyond the proved cases, and the numerical evidence is consistent with the conjecture always being true. But numerical evidence, as we have seen many times tonight, is not proof. And now, let's look at something grand, something that has been shaping mathematics for over 50 years and is not a single problem, but a whole web of them. In 1967, Robert Langlands, a young Canadian-American mathematician, wrote a letter to André Weil, one of the greatest mathematicians of the 20th century. In that letter, Langlands sketched a set of conjectures that he described with characteristic modesty as a bunch of speculative guesses. Those conjectures have grown into something called the Langlands program, which is now arguably the largest and most ambitious project in all of contemporary mathematics. The Langlands program proposes a vast web of deep connections between several apparently unrelated areas of mathematics. On one side is number theory, specifically the theory of automorphic forms, which are certain highly symmetric functions that live on complicated spaces. On another side is representation theory, which studies how abstract algebraic structures can act on vector spaces. Threading through everything is the theory of generalized versions of the Riemann zeta function, adapted for specific mathematical contexts that keep showing up whenever mathematics gets deep enough. Langlands conjectured that certain symmetric objects on one side correspond in a precise and calculable way to other objects on the other side. This correspondence, if fully established, would unify enormous swaths of mathematics. It would explain why Weil's proof of Fermat's last theorem, which used elliptic curves and modular forms, worked in the way it did. Weil's proof was essentially a proof of a special case of the Langlands correspondence, but most of the program remains conjectural. There are specific cases that have been proved, sometimes after decades of work by large groups of mathematicians, but the full program in its most general form is still a horizon rather than a destination. In 2018, Langlands was awarded the Abel Prize for the depth and breadth of his vision. His letter from 1967 has guided mathematics for more than 50 years. One way to understand the scope of the Langlands program is to realize that it connects two areas of mathematics that appear completely unrelated. Number theory is about whole numbers and their properties. Representation theory is about symmetry, about how abstract groups of symmetries can act on spaces. These sound like different subjects in completely different parts of mathematics. The Langlands program says they are secretly the same subject, written in two different languages. The specific correspondence involves something called automorphic forms on one side and Galois representations on the other. Automorphic forms are functions defined on certain highly symmetric spaces. They are related to things like modular forms, which are functions on the complex upper half plane with very rich symmetry properties. Galois representations describe how the symmetry group of all algebraic numbers acts on vector spaces. They encode arithmetic information about number fields in an algebraic way. Langlands said there is a correspondence between these two kinds of objects. Every automorphic form has a Galois representation associated to it, and every Galois representation of the right kind has an automorphic form associated to it. They are two faces of the same mathematical coin. The reason this is so powerful is that automorphic forms are very amenable to analytic techniques. You can study them using tools from analysis, from the theory of differential equations, from the geometry of symmetric spaces. Galois representations, on the other hand, are amenable to algebraic and arithmetic techniques, so the correspondence allows you to take a hard number theoretic question, translate it into an analytic question using the correspondence, solve it there using analytic tools, and then translate the answer back. This is exactly what Wiles did, in essence, when he proved Fermat's last theorem. The program has been gradually extended over the decades, made more precise, generalized to new settings. There is a geometric version called the geometric Langlands program. There is a version over function fields instead of number fields. There are local versions and global versions. Each extension is a research program in itself, requiring years of work to even formulate precisely, let alone prove. Okay, and now let's look at something from topology. You might have heard that the Poincaré conjecture was proved by Grigori Perelman in 2002 and 2003. Perelman proved it, and it became the only Millennium Prize problem to be solved. He also turned down the Fields Medal and the $1 million prize, which made him, briefly, the most famous mathematician on the planet and generated enormous amounts of press attention that he seemed to actively not want. The Poincaré conjecture that Perelman proved was about three-dimensional shapes, but there is a cousin of this problem in 4 dimensions, and it is still open. It is called the smooth 4-dimensional Poincaré conjecture. It asks whether there is only one smooth structure on the 4-dimensional sphere. A smooth structure is a subtle concept. A shape can have multiple inequivalent smooth structures. That is, the same underlying topological shape can be made smooth in different, non-equivalent ways. In all other dimensions, the 4-sphere has a unique, smooth structure. In dimension 4, we do not know whether exotic smooth structures can exist on the sphere. This is deeply strange. Dimension 4 is special in many ways in mathematics. Many phenomena that are smooth and controllable in all other dimensions become wild and irregular in 4 dimensions. The discovery in the 1980s that 4-dimensional space itself can have infinitely many exotic smooth structures was one of the most startling revelations in the history of geometry. But whether the force sphere specifically can have an exotic smooth structure is still not known. Now let's look at a problem in graph theory. A graph is a collection of dots, usually called vertices, and lines between pairs of them, usually called edges. Coloring a graph means assigning colors to the vertices so that no two adjacent vertices, no two connected by an edge, share the same color. The chromatic number of a graph is the minimum number of colors needed to do this. A click in a graph is a subset of vertices that are all mutually connected. Every pair of vertices in the click is joined by an edge. A clique with k vertices clearly needs k colors, since every pair is adjacent. Hugo Hadwiger, a Swiss mathematician, conjectured in 1943 that if you cannot color a graph with fewer than k colors, then it must contain a certain type of reduced subgraph called a minor that looks like the complete graph on k vertices. A minor is a graph obtained from a subgraph by contracting some edges, merging their endpoints into single vertices. For small values of k, the conjecture has been proved. For k equals 5, it is equivalent to the four-color theorem, which says that maps on a plane can always be colored with four colors such that no two neighboring regions share a color. The four-color theorem itself was proved in 1976 by Appel and Haken using a computer in a proof that checked thousands of configurations. It was controversial because it was the first major theorem to require a computer for verification. For k equals 6, Hadwiger's conjecture was proved in 1993. For k equals 7 and beyond, the conjecture remains open. And now let's look at something about the Ramsey numbers. This story starts with the result proved by Frank Ramsey in 1930. The result says, informally, that in any sufficiently large structure, you are guaranteed to find some kind of ordered substructure. Order emerges inevitably from largeness. The classic example is about parties. If you have at least 6 people at a party, it is guaranteed that there are either 3 mutual acquaintances or 3 mutual strangers. Among any 6 people, this must be true. With 5 people, it is not necessarily true. These guarantees, called Ramsey numbers, represent the minimum size a structure needs to be before a specific type of order is guaranteed. The Ramsey number of 3 and 3 is 6. What about the Ramsey number of 4 and 4? The minimum number of party guests such that you are guaranteed either 4 mutual acquaintances or 4 mutual strangers? That number is 18. This was proved in 1979. What about the Ramsey number of 5 and 5? Nobody knows. The best current bounds say it is between 43 and 48, somewhere in that range. Despite decades of work, nobody can pin down the exact value. Erdős once said that if an alien species arrived and demanded to know this number within a year, or they would destroy the planet, we should devote all of humanity's computational resources to the problem and might just barely succeed. But If they demanded the Ramsey number of 6 and 6 in the same time frame, he said we would have no chance. Ramsey numbers grow incredibly fast, and computing even small ones exactly seems to require searching over structures of a size that is computationally out of reach. To understand just how fast they grow, think about it this way. The Ramsey number of 3 and 3 is 6. The Ramsey number of 4 and 4 is 18. The Ramsey number of 5 and 5 is somewhere between 43 and 48. The Ramsey number of 6 and 6 is somewhere between 102 and 165. These are modest numbers. They fit on a single line. But the Ramsey number of 10 and 10 is somewhere between 779 and 2,392. And by the time you get to the Ramsey number of 20 and 20, the upper bound is so large that writing it out in ordinary notation would fill a book. The gap between the upper and lower bounds grows along with the numbers. For the Ramsey number of 5 and 5, the gap is just 5. For the Ramsey number of 10 and 10, the gap is over 1,500. The problem gets harder, faster, then the numbers get bigger. Frank Ramsey himself was an extraordinary figure. He was a British philosopher, economist, and mathematician who made major contributions to all three fields before his death at the age of 26. He proved his combinatorial result, the one at the root of all of this, almost as a footnote to a paper about logic. He was not primarily a mathematician in the narrow sense. He was someone who moved easily between fields and found profound things wherever he looked. The field of Ramsey theory, named after him, is one of the most active areas in modern combinatorics, and the central questions in it, like determining exact Ramsey numbers, remain stubbornly resistant despite the effort of many people over many decades. Next, let's look at a question about prime numbers that is so simple to state that it is almost insulting and yet has been sitting there unanswered for a long time. A Mersenne prime is a prime number of the form 2 to the n minus 1. So 2 to the 2 minus 1 is 3, which is prime. 2 to the 3 minus 1 is 7 prime. 2 to the 5 minus 1 is 31 prime. 2 to the 7 minus 1 is 127 prime. But not every number of this form is prime. 2 to the 4 minus 1 is 15, which is 3 times 5, not prime. The question is, are there infinitely many Mersenne primes? The current answer is we do not know. Currently, the largest known prime numbers are Mersenne primes. The great internet, Mersenne Prime Search, a distributed computing project involving volunteers around the world running software on their personal computers, has been finding Mersenne primes for decades. As of recent years, The largest known, Mersenne prime, has over 24 million digits. Every time a new one is found, it is a genuine event in the mathematics and computing community. These numbers are vast beyond imagining. A number with 24 million digits, written out at normal font size, would stretch for kilometers. To read it aloud, 1 digit per second, would take years, but finding more of them is not the same as proving there are infinitely many. We have a heuristic argument suggesting there should be infinitely many, based on how quickly numbers of this form grow and how likely numbers that large are to be prime, but a proof is not available. Part of why this is hard is that whether a number of the form 2 to the n-1 is prime depends very sensitively on n. If n itself is not prime, then 2 to the n-1 is definitely not prime. If n is prime, then 2 to the n-1 might or might not be prime, and there is no simple rule for which the primes n for which 2 to the n-1 is also prime are called Mersenne prime exponents, and their distribution is not understood. The largest known Mersenne prime exponents are scattered seemingly at random among the prime numbers. There is no formula predicting which prime n will give you a Mersenne prime. You have to check each one, and checking whether a number with 20 million digits is prime is an enormous computational task, even with the most efficient algorithms available, even on the most powerful hardware. Mersenne primes are also connected to another ancient mathematical object, perfect numbers. A perfect number is a number equal to the sum of its proper divisors. 6 is perfect because 1 plus 2 plus 3 equals 6. 28 is perfect because 1 plus 2 plus 4 plus 7 plus 14 equals 28. The ancient Greeks were fascinated by perfect numbers and gave them a kind of mystical significance. Euclid proved that whenever 2 to the n-1 is prime, the number 2 to the n-1 times 2 to the n-1 is perfect. So every Mersenne prime gives you a perfect number. Whether there are infinitely many even perfect numbers is equivalent to whether there are infinitely many Mersenne primes, and whether there are any odd perfect numbers is an entirely separate open question that has been investigated for centuries, with no odd perfect number ever found and no proof that none can exist. And let's look at one more. In 1966, Mark Kac wrote a famous paper asking, if you listen to the sounds produced by a drum and you know the frequencies of all the harmonics, can you determine the exact shape of the drumhead? Mathematically, this is a question about whether the eigenvalues of a specific differential operator on a region uniquely determine the region up to rigid motions. The eigenvalues correspond to the frequencies of vibration. For a long time, people thought the answer might be yes. But in 1992, 3 mathematicians constructed 2 different drum shapes that have exactly the same eigenvalue spectrum, 2 completely different shapes that sound identical. So the answer to Kak's question for general drums in the plane is no. You cannot always hear the shape, but the deeper mathematical questions are more nuanced. For drums in 3 dimensions, or for surfaces with curvature, or for drums satisfying certain additional conditions, the question of whether the spectrum determines the shape is still partially open. The detailed question of how much geometric information is encoded in eigenvalues is a rich and active area of research. And then there is a problem in 2004 that became one of the greatest breakthroughs of that era. Ben Green and Terence Tao proved that the prime numbers contain arithmetic progressions of every finite length. An arithmetic progression is a sequence of numbers where each one is the same fixed amount more than the previous one. 3, 7, 11 is an arithmetic progression with common difference 4. The primes, Green and Tao proved, contain arithmetic progressions of length 3, of length 4, of length 5, of length 1,000,000, of any length you like. This was a stunning result. It said that despite the apparent randomness of the primes, they have this deep internal structure. You can always find somewhere out in the vastness of the prime numbers a sequence of primes spaced perfectly evenly apart, no matter how many terms you want. There is a prime arithmetic progression of length 5. There is one of length 1,000. There is one of length 1,000,000. They are out there. You may have to go incredibly far out along the number line to find them, but they exist. The proof used a remarkable mixture of techniques from number theory, from harmonic analysis, and from a then new area called additive combinatorics. It drew on ideas that came from ergodic theory, which is the study of the long-term behavior of dynamical systems, and specifically from a deep theorem of Semeredi about dense sets of integers. The proof was itself a major achievement in the interweaving of different mathematical fields, and it pointed toward an entire research program that is still developing. But this result, as beautiful as it is, leaves many things unanswered. We do not know whether the primes contain infinite arithmetic progressions that go on forever. The Green-Tao theorem only guarantees arbitrarily long finite ones, not infinite ones. And the broader question of the structure of gaps between primes remains wide open. The Riemann hypothesis, if proved, would tell us a lot about these gaps. It would bound the error in our estimates of how many primes there are up to a given number, which would in turn constrain where primes can and cannot appear. But even with the Riemann hypothesis, many questions about the distribution of prime gaps would remain, and now there is something worth sitting with before we are done, something that floats above all of these specific problems and gives them an extra layer of strangeness. When mathematicians talk about proving something, they mean something very specific. They mean writing a sequence of logical steps, each one following necessarily from the last, starting from accepted starting assumptions, leading to the desired conclusion. A proof is not a matter of opinion. It is not a matter of evidence or experiment. It is a matter of logic. A proof that is wrong is not a proof. A proof that has a gap is not a proof. There is a cleanness, a finality to a true mathematical proof that nothing else in human knowledge quite has. Once something is proved, it is proved forever. The theorem does not expire. It does not get revised when new data comes in. It is done. But in 1931, Kurt Gödel, a 25-year-old Austrian mathematician, proved something that shook the entire edifice of mathematics to its core. He proved that any consistent formal system, any set of starting assumptions strong enough to describe the basic arithmetic of whole numbers, must contain true statements that cannot be proved within that system. This is the Incompleteness theorem. It says that truth is bigger than proof. There are mathematical facts that are true but cannot be derived from any given fixed set of starting assumptions. Gödel's proof is itself a masterpiece of mathematical ingenuity. He essentially taught arithmetic to talk about itself. He found a way to encode statements about arithmetic inside arithmetic itself, so that you could write down using ordinary numbers and arithmetic operations a statement that says, in effect, this statement cannot be proved. If the system is consistent, it cannot prove that statement, but the statement is true, so the system is incomplete. This encoding trick, now called Gödel numbering, assigns a unique number to every symbol, every formula, every proof in the formal system. Then statements about proofs become statements about numbers, and the self-referential loop becomes possible. The theorem came as a genuine shock to the mathematical world. David Hilbert, the great mathematician whose program at the start of the 20th century had aimed to put all of mathematics on a secure, complete, and consistent axiomatic foundation, had been working toward exactly the opposite conclusion. The Gödel incompleteness theorems, proved in the very year Hilbert formally stated his program, showed that the goal was unreachable. No formal system could capture all mathematical truth. The foundation would always have gaps. This immediately raises a haunting question about the problems on our shelf. Could some of them be true but unprovable? Could the Riemann hypothesis, for example, be true but simply beyond the reach of any proof system? Most mathematicians believe this is unlikely for the specific problems we have discussed. There is a technical reason why the Riemann hypothesis, if unprovable, would actually have to be true. If it had a counterexample, we could find it computationally. If it has no counterexample, then it is true. So the Riemann hypothesis cannot be false and unprovable. It either has a proof or a disproof, or it is true and unprovable. The third option, true and unprovable, is genuinely possible, and it would mean that the mathematics we have is simply too weak to see the full structure of the primes. We already know this happens. The continuum hypothesis, which asks whether there is an infinity between the size of the whole numbers and the size of the real numbers, was proved by Gödel to be consistent with the standard starting assumptions of set theory, and then proved by Paul Cohen to have its negation also consistent. Both possible worlds are equally valid. The question is not answered by the mathematics we have. It is genuinely, provably outside its reach. The consistency proofs use a technique where you construct a model of set theory, a mathematical universe, in which the hypothesis holds. Then you construct another model where it fails. Both models satisfy the same starting assumptions. So the starting assumptions cannot determine which world is real. This is philosophically very deep. It means the question of whether there is an infinity between the counting numbers and the real numbers is not a question that has a unique answer within the mathematics we have built. It depends on which mathematical universe you are in, and the starting assumptions of set theory as currently formulated do not pin down which universe is the right one. Could the same be true for P versus NP, for the Birch and Swinnerton-Dyer conjecture, for Goldbach? We do not know. And this is one of the deepest and most uncomfortable questions in all of mathematics. It sits quietly underneath everything. Most mathematicians work with the faith that the problems they are working on are solvable, that the answers exist within reach of some extension of the tools we have, that mathematics is not broken, just incomplete. And this faith has served mathematics well. Every decade, things that seemed hopeless get proved. Every generation, the frontier moves, but the possibility remains. Some of the books on the shelf might have pages that are, in some deep sense, blank. Not blank because nobody has written on them yet. Blank because the ink we have access to cannot make marks on that particular kind of paper. The answer is there, in some sense, but we may not be able to reach it from where we stand. So that is the shelf, or at least the part of the shelf we can visit tonight. These problems range from things you could explain to a 10-year-old, like Goldbach's conjecture or the Collatz conjecture, to things that require decades of study to fully appreciate, like the Langlands program or the Young-Mills mass gap. They range from problems that are 200 years old to problems formulated in the last 50 years. They come from number theory and topology and combinatorics and analysis and physics and computer science. They span the entire landscape of mathematics. What they have in common is that they are all genuinely hard. Not hard in the way that a complicated calculation is hard, where you just need time and patience. Hard in the sense that nobody currently knows what kind of mathematics would be needed to solve them. Hard in the sense that the tools that exist do not reach, but there is something else they have in common. They are all the right questions. That is the most important thing about them. Each one of these problems, however old or new, however famous or obscure, is asking about something that goes to the root of how numbers and shapes and logic work. These are not arbitrary puzzles that happen to be posted somewhere. They are questions that keep appearing from different directions whenever people press hard enough on the structure of mathematics. They are cracks in the wall of what we understand, cracks that keep appearing in the same places no matter how we approach them. And that consistency, that stubbornness, suggests that the cracks are pointing at something real, something underneath. And perhaps the most remarkable fact of all is that we have no idea when any of them will be solved. Some of them might fall in the next 10 years. There have been periods in mathematics where a single breakthrough idea resolved problems that had been open for centuries. The proof of Fermat's last theorem came after 358 years of waiting. The proof of the four-color theorem came after 124 years, and even then it required a computer in a way that made people uncomfortable. The proof of the Poincaré conjecture came after 100 years, from a man working largely alone in St. Petersburg, who then turned down all the prizes for it. Mathematics does not follow a schedule. Solutions do not arrive when expected. They arrive when the right person with the right preparation finds the right angle of attack on the right problem at the right moment. Sometimes that moment comes quickly. Sometimes it takes centuries. There is no way to predict which. Somewhere, right now, someone is probably working on one of these problems. Maybe in a university office late at night, the kind of office with a whiteboard covered in symbols and a coffee cup that has been cold for 2 hours and a view of a parking lot that nobody looks at. Maybe at a kitchen table. Maybe in a collaboration spread across 3 countries, in a thread of emails that has been going for 2 years. Maybe in the mind of a graduate student who does not yet know that the thing they are thinking about is connected to something that has been open for 160 years. The problems are still there, waiting. They have been patient for a long time. They do not mind waiting a little longer. There is a strange kind of comfort in that, in the idea that the universe contains these deep structures, these patterns and regularities and truths that exist whether we know them or not, that 2 + 2 was equal to 4 before there were humans, that prime numbers existed and were prime before anyone counted them, that the zeros of the Riemann zeta function were sitting on their line, or perhaps one was not, for billions of years before Riemann sat down to think about them. The questions are not going anywhere. The answers are out there. We just have not found the right language yet. And that is perhaps the most human thing about mathematics, that we keep reaching for things we cannot quite touch, and finding unexpected beauty in the reaching itself. Every generation looks at this shelf and picks up a book and tries. Every generation adds a little to what we know, and every generation puts the book back, still not finished, still full of mystery, ready for the next person who comes along in the quiet and decides to try. And tonight, in this warm, quiet library, we can sit with the not knowing. Let it be strange and beautiful. Let it be peaceful. The shelf goes on. The questions keep watch. And somewhere out there, in some mathematician sitting quietly with a notebook and a cold cup of tea, the next answer is already forming, finding its shape in the dark, waiting to be seen. And just like that, the library is very still. The amber light is warm. The shelf is very long. The whole of mathematics is sitting there quietly in the dark, enormous and patient, and full of things we have not found yet, and that is more than enough to carry into sleep. The problems are still there. They always will be.